Hey guys, in this course on the electromagnetic waves, we're going to discuss how the idea of electromagnetic waves emerged and originated in the minds of scientists who even predicted its existence before they were produced experimentally in the laboratory. Let me introduce myself briefly again. I'm Sameep Villani. I'm an educator by passion. I promote extracurricular learning and active visualization exercises to augment the understanding about each concept. I believe clear understanding should help you solve all related problems, provided that you have enough practice and enough amount of reading to back you up. If you like my courses, if you like the lessons, I request you to please follow me, rate my work, give your reviews, express your pleasure by going through this link given at the bottom, because your enthusiasm is contagious. Our story begins in medieval Europe in 19th century. The time is somewhere around 1820s. We are at the University of Copenhagen in Denmark, and we are experiencing one of the lecture demonstrations of the Daft Dane, or how his students knew him as Professor Hans Christian Ørsted. He had recently noticed some very interesting phenomena that he wants to share with the students. And this is how he does it. The magnetic needle suffers deflection from its natural north-south orientation when an electric current is passed through a metallic wire kept in its vicinity. The metallic wire given current by the battery. This is the magnetic needle. The magnetic needle is seen to deflect if there is a current passing through this wire. Now this is Hans Christian Ørsted. Upon experimenting further, I was also able to conclude that the magnitude of this effect is proportional to the amount of current flowing in the wire, as well as the effect goes down, it reduces with the increasing distance between the wire and the needle. And you can see this effect even if I use another material for the wire, whether it's copper, aluminium, steel, or what say you will still see this effect. So it proves that this is not a material specific phenomena, but it depends highly on the current passed through the coil or through the wire. Now, as you might know, Hans Christian Ørsted is one of the pioneers of the unification of electricity and magnetism into one overarching umbrella topic, electromagnetism. His results were noticed by a Frenchman whom we shall call the fervent French, or you can also call him André-Marie Ampère. He was inspired by Monsieur Ørsted's demonstration of a yet unexplained manifestation of a strange magnetic effect due to an electric current flowing through a conductive wire. He decided to see the effect that one current-carrying rod, CD, this is the apparatus that he designed and made in order to prove how one current-carrying wire, CD, would affect another current-carrying rod, EF there, which this current-carrying rod, CD, is suspended by two fixed points, supports S and T. He was astonished to discover that these current-carrying wires behave in conflict with the behavior of electrostatic charges. Now, if there are currents flowing in the wire, there are charges flowing with respect to time in the wire. Now, we know that like charges repel, but unlike charges attract each other. That is, positive, positive repel, negative, negative repel, positive, negative attract. On the other hand, when both rods carried current in the same direction, they attract each other and they repel each other when the current is passed in opposite directions. Now, this was noticed by Ampere in his experiments, and he wanted to give this result a mathematical formulation. This was the first realization of Lorentz force, and Ampere went on to develop a mathematical law to quantify the magnetic field which is produced around the current carrying conductor. This gave rise to Ampere's circuital law. Our next character in the story is the enchanting English. He is one of my favorite scientists of all time, Michael Faraday. He notices that Mr. Ørsted has shown that a wire carrying a steady current is perhaps throwing out an invisible electric force, actually a magnetic field, which was shown by him to go around the cylindrical wire in circles. At the time in 1830s, people did not have a clear idea of what a field is, or they thought that forces only act at contact and they do not act at a distance. Although the notion of gravity was there, but people did not know how the gravitational force was propagated from the source to another object with which it is interacting. So there is something which is needed that transports this magnetic, electric, or gravitational, or what say you, that this force which was proposed by Faraday as a field, usually denoted by field lines in space. Ørsted showed that an electric current is seen to produce a magnetic force around the electric current carrying wire. Could it be that a uniform magnetic field could produce a steady current? Or perhaps a time-changing magnetic field? He tried to test this using an apparatus called a Faraday coil by us nowadays, and this is something which he even holds in his hands in this statue of him. That's Michael Faraday. What he tried to do is he passed an electric current in a coil, a solenoid. A solenoid was first invented and named by André Marie Ampère, which we were introduced to just before Faraday. He passes current through this solenoid on this side of this toroidal ring, and as a result, he knew that because of this electric current, he would have a magnetic field produced. And if a uniform magnetic field produces an electric current, the magnetic field is going to transport its energy to this coil on the other side, which he connected to a galvanometer. Or we would do it with a multimeter these days, but galvanometer. When current is flowing when current is flowing through this coil on the right, there is no current which he observed to be that was induced on the left hand side coil. But this is the experimental arrangement that he used. It was only that when he closed the switch or opened the switch, that is when he just started passing current or just stopped passing current through this coil on the left, that he saw an EMF produced on the other side of the coil. This was mutual induction, which is a concept we will learn later in other courses. An EMF and a current is induced in the opposite coil only when the circuit is switched on or switched off, or when there is a change in the magnetic field produced by the left hand side coil. It was only then an electric current was induced, which was measured by the galvanometer. Now, knowing these results, we needed another character to come into the picture, which we shall call the shrewd Scottish, or James Clerk Maxwell. These equations, these four equations at the bottom, enshrine his major work during his life, his short life of around 48 years. He died pretty young. He noticed that it appears that Mr. Ampere's mathematical formulation of determining what a magnetic field will be around a current carrying wire, it needs reformulation. Now, Ampere gave the law which had only the left-hand side term in this fourth equation and the first right-hand side term. It did not have this term, which was included by Maxwell himself as a correction to Ampere's circuital law, which gave rise to Ampere-Maxwell law, and which finished the unification of electricity and magnetism at the end. He noticed that the generality of choosing an open surface attached to the closed loop around which we are trying to measure the magnetic field is suffering here, because there were instances when, even if the magnetic field is not supposed to be zero around a current carrying wire, a certain choice of an open surface attached to the closed loop was giving us zero under very special circumstances, not always. So the generality of choice of an open surface was suffering here. So what we need is a displacement current in addition to the actual current. In cases where a transient current gives rise to a time-changing electric field, as in the case of a capacitor being charged or discharged. Possibly, a time-changing electric field could possibly generate a magnetic field. Apart from just a current-producing magnetic field, could a changing electric field produce a magnetic field? Yes, it does, and he was able to prove this, both theoretically and experimentally. But he also noticed, do these equations tell us much more or anything more than what they appear to show on the surface? Is there anything deep inside that is yet to be found out? Do these equations convey something more? How is that? That is a question which I want you to ponder about. And I want you to go through the exercise because this is important for you. Brainstorming and thinking are few of your major skills that you must hone in time to develop yourself. Thank you for listening.